In 1915, Albert Einstein published the general theory of relativity. Soon after, Karl Schwarzschild found exact solutions to Einstein's field equations, which predicted objects with strong enough curvature of space-time where not even light could escape. These objects are now known as black holes. However, this was not the first time a black hole-like object was predicted to exist. Back in 1783, a man named John Mitchell predicted that a star with a strong enough gravitational field, where not even light could escape, might exist. Since no light could escape its grasp, it would be invisible or dark, hence the name dark star. To understand how John Mitchell came to the realization that dark stars could exist, it is important to understand a few key concepts in physics. The first concept is the particle theory of light. This was the dominant theory of the composition of light in Mitchell's day, which was popularized by Isaac Newton. This theory states that light is composed of tiny, discrete particles similar to that of matter. These corpuscles, as they called them, would travel in straight lines at a finite speed. If these corpuscles were within a gravitational field, their velocity could be slowed or altered just like normal matter. When a corpuscle escapes the surface of a star, for example, it would be slowed down by the gravitational field of that star. The next concept is escape velocity. Escape velocity is the minimum initial speed an object, such as a rocket, must be moving in order to escape the gravitational field of another object, such as the Earth. Any body of mass has its own precise escape velocity, which can be calculated. An object's escape velocity is proportional to the square root of its mass divided by its circumference. Thus, if mass is constant, the smaller the circumference, the larger the escape velocity. The reason why escape velocity increases as its circumference decreases with constant mass is because as the circumference decreases, the surface becomes closer to the center of mass. If the surface is closer to the center of mass, then any object on that surface is deeper within the gravitational field compared to an object of the same mass but larger circumference. Since the object is deeper within the gravitational field, it would require greater velocity to escape the surface. But what if an object, such as a star, was at the critical circumference, which is the circumference at which the escape velocity equals the speed of light? At this circumference, nothing but light could escape the gravitational pull of the star. But if the star was below the critical circumference, not even light could escape the grasp of the star. Mitchell calculated what the critical circumference would be for a star the mass of the Sun, which is approximately 18.5 kilometers or 11.5 miles. To bring these concepts together, imagine a star that is below the critical circumference for its given mass. Its escape velocity would therefore be greater than the speed of light. Now imagine corpuscles of light being emitted at the surface of the star. Since the particle's velocity is below the minimum velocity required to escape the star, the particles would reach a maximum height and then begin to fall back to the surface. Therefore, to an outside observer, the star would appear dark. This is precisely what a dark star is, a star that is below the critical circumference for its given mass, where the star's escape velocity exceeds the speed of light. Since no light can escape its surface and arrive at Earth, it appears completely invisible except for its gravitational influence upon other objects. Mitchell also predicted how an astronomer might find a dark star. If a normal star and a dark star were in a binary system, that is, if they orbited each other, then it would appear as if the visible star were orbiting an invisible mass. Through observations of the visible star's orbit, an astronomer could calculate the mass of this dark star using Newtonian mechanics. This prediction turned out to be extremely accurate to how modern-day astronomers have found black holes, including the supermassive black hole at the center of the Milky Way galaxy. In many ways, a dark star is like a black hole. Both objects have an escape velocity greater than the speed of light. Both are massive objects that appear invisible, yet can still be detected by their gravitational fields. Yet there are a number of key differences that must be pointed out. First, dark stars are simply ordinary stars that happen to be massive enough to keep light from escaping its gravitational field. However, according to general relativity, black holes are regions of space-time that contain a singularity at its center and an event horizon at its edge. This region of space-time is warped by the dense singularity to such an extent that not even light travels fast enough to escape. Second, black holes don't just affect space but also time. As an object approaches a black hole, time itself begins to slow down. This is known as time dilation. Dark stars, since they are Newtonian in nature, do not have any effect on the passage of time. Third, a dark star is a concept derived from Newtonian mechanics, whereas a black hole is a concept derived from general relativity. In Newtonian mechanics, such a massive star could conceivably exist. However, in general relativity, the star would have collapsed in on itself, forming a black hole. The list of differences could go on, but these are a few of the most notable. Even though these two objects have similarities, they are distinctly different from one another. Science is complicated. It's not a linear progression of ideas building off of one another, approaching an ever more accurate picture of reality. It is a branching tree with many right and wrong paths. We often abandon a path just to revisit it in the future. Sometimes we stumble upon an idea that gets drowned out by other issues of the day that don't resurface until centuries later. Sometimes the ideas we pursue leave us at a dead end, whereas others open new paths we could have never imagined existed. We can be blinded by our arrogance in thinking we understand how our universe works, when in reality one small problem could unravel what we thought we knew. Black holes were once discovered and forgotten about, just to be rediscovered by a later generation of thinkers. It makes you wonder what other ideas of our past we might have forgotten, and one day will rediscover.